the Anthropic benchmark. A specific target sentence is placed inside a 200,000 token context window. The model has full access to the text. Its retrieval accuracy is 27%. Then a single instruction line is added to the prompt.
Accuracy jumps to 98%.
The target sentence did not move. The model did not get smarter. Something else changed. If you deploy these systems, this failure highlights a fundamental misconception about context windows.
If the information was present but unfound, that sounds like a retrieval problem. It does not sound like a fundamental model problem. I mean, if a system fails to locate a target within a large dataset, the search mechanism is usually the point of failure.
That relies on a flawed assumption about how models access information. The context window is commonly treated as a filing cabinet where all information sits with equal accessibility. It is not a filing cabinet.
A filing cabinet implies neutral storage. You open a drawer and the file is there, exactly as accessible as the file next to it. Memory, in the cognitive sense, operates similarly, subject only to forgetting over time.
The context window operates entirely differently. It is the spotlight. The distribution of that light is controlled entirely by position, not by relevance.
So the model illuminates some parts of the input more than others. The spotlight is brighter in certain areas regardless of what information sits in those areas.
What the model can see is not the same as what it will actually use. We define a context window as the amount of text a language model can process in a single forward pass. Everything the model can see when generating a response sits inside this window.
This includes the prompt, the conversation history, retrieved documents, and system instructions. If information sits outside the context window, the model cannot access it.
If it sits inside, the model can, in principle, use it. But that qualifier is doing considerable work. The term shaping this failure is transformer attention, specifically a mechanism called causal masking.
We must look at how models process sequences to understand the spotlight. Models generate text to left to right. A token can only attend to the tokens that appeared before it.
This is a structural requirement for text generation. A token cannot attend to words that have not yet been written. Every token in a sequence queries the tokens before it to weight their relative importance.
The consequence of that left-to-right processing is where the positional bias begins.
Earlier tokens accumulate attention weight simply by having more opportunities to be referenced. They do not accumulate this weight because they matter more to the query.
They accumulate it purely because of sequence mathematics. Token number 1 can be attended to by every subsequent token in the sequence.
Right. If the sequence is 100,000 tokens long, token 1 participates in 100,000 calculations. It has 100,000 chances to influence the generation path.
Token number 50,000, sitting in the exact middle of the prompt, can only be attended to by tokens 50,000 and onward. It has half the opportunities to accumulate attention weight compared to the first token.
The outcome of this geometry is the lost in the middle problem. The beginning and end of the context receive disproportionate attention. The early tokens receive attention due to this causal accumulation.
And the end of the context receives attention because it is the most recent. It sits directly next to the generation step.
The result is a strict U-shaped attention curve. The middle of the sequence is structurally disadvantaged regardless of what it contains. In 2023, Stanford researchers mapped this empirically.
They took standard models and asked them to extract specific facts from long documents. They systematically moved the target fact from the beginning to the middle to the end of the prompt.
They showed a severe performance drop the moment key information was slid into the center of the sequence. The information was present, the model had access to it, it was simply less likely to use it because of its position.
If you feed an AI 50 pages of medical records and the crucial contraindication is on page 25, that clause sits at the bottom of the curve. But if it is a structural disadvantage, does that imply it is permanently broken?
It stands to reason this fixes itself with better training data or in newer model architecture. That is the working assumption in the industry. Newer models update their architectures constantly.
June 2025 MIT research addresses that assumption directly. They trace the cause to causal masking and positional encoding using a graph-based theoretical framework.
This bias is present at initialization before training even begins. It is not a learned behavior that can be unlearned through a broader data set. It is a geometric property of how causal decoders process sequences. It is an architectural reality.
Right, and that doesn't fix itself.
Crucially, a larger context window does not flatten the U-shaped attention curve. It merely stretches it.
A 1 million token context window does not provide equal retrievability across 1 million tokens. The model will reliably process the beginning and end of that massive window.
It will process the middle with decreasing fidelity the further from the edges it sits. This changes the operational reality for deployment decisions. It brings us to what this means for enterprise AI and retrieval-augmented generation systems.
Standard ARG patterns heavily prioritize the retrieval step. The process is straightforward. A user asks a question, the system queries a database, retrieves a set of relevant documents, concatenates them, and passes them to the model.
Engineering effort goes entirely into hybrid search, embeddings, and re-ranking. The entire industry focuses on making sure the database surfaces the correct text. That focus makes logical sense initially.
Well, if you do not retrieve the correct document, the generation step cannot possibly succeed. The retrieval step is necessary.
But it is completely insufficient if the geometry works against it. If your re-ranker perfectly surfaces the 10 most relevant documents, the system frequently still fails. The retrieval quality is strictly bounded by what happens after retrieval.
If the retrieval is perfect and the documents are placed in the context window, why does the system fail? The model has the exact information required to answer the query. It is sitting right there in the prompt.
Because the ordering of retrieved context is a critical engineering variable. Most pipelines treat it as irrelevant. They concatenate the documents chronologically or by search score and pass them to the model without regard for sequence position.
If a re-ranker surfaces the right document and then places it at position 6 of 10, it has done half its job. The document falls directly into the trough of the U-shaped attention curve.
It is structurally disadvantaged before a single token is generated. The model is less likely to weight that document appropriately. This happens not because the document is less relevant, but because of where it sits in the sequence.
The retrieval was correct. The injection was not.
3 variables govern how well a model uses retrieved context. Retrieval quality is the first. The second is ordering, which determines where in the sequence the most relevant material sits.
The research treats this as a design principle. The most relevant retrieved document should sit at the beginning or the end of the injected context. This is not because it is aesthetically tidy.
It is because the attention architecture will systematically underweight anything placed in the middle.
Okay, that changes the question. If ordering is the primary issue, why not simply bypass the ordering problem by passing in everything?
The context windows are massive now. If the window holds 200,000 tokens, you do not need to filter down to 10 precise documents. Which brings us to the third variable, density.
It also triggers the distractor problem. Related but irrelevant content does not sit quietly in the background. It actively competes for attention.
If you ask an AI about third quarter revenue and provide 10 documents mentioning first, second, and fourth quarter revenue, those documents are not neutral. An LLM processing a long context is not filtering information before it reasons over it.
It attends to everything simultaneously. It weights everything by a combination of position and learned semantic association.
The model's weighting mechanism cannot cleanly distinguish between a document that is about the right topic and a document that contains the exact right answer. They share semantic similarities in the vector space.
Which is the more expensive version of the problem. So a relevant document buried in the middle of adjacent noise faces 2 distinct penalties.
It faces a multiplicative penalty. Positional underweighting combined with semantic competition. Every token of context that is not directly relevant to the query acts as a tax on the model's reasoning capacity.
Filling a 200,000 token window to capacity makes it less reliable, not more.
It becomes less reliable precisely in the cases where the answer is buried in the middle and surrounded by plausible alternatives. Density requires deciding what to exclude rather than what to include.
A smaller, tighter context of genuinely relevant material will outperform a larger context padded with non-essential documents. We need to loop back to the Anthropic benchmark you opened with.
A target sentence placed in a 200,000 token window, 27% accuracy.
1 instruction line added, 98% accuracy. This complicates your structural argument.
Go ahead.
If the model is fundamentally geometrically biased against the middle, why did adding the phrase, "here's the most relevant sentence in the context," fix the accuracy? The target sentence was still in the middle. The geometry did not change.
The geometry did not change, but the attentional anchor did. Models treat instructions and content differently based on their position in the sequence.
They treat them differently because of where they sit, not because they are semantically different from the surrounding text.
When Anthropic added that line, they did not change what the model knew. They placed an attentional anchor in a structurally privileged position. Instructions that appear in early salient positions receive the positional advantage that early tokens always receive.
Salient positions like the system prompt or the beginning of the user turn, they are attended to by the entire subsequent sequence.
Those salient positions redirect the model's weighting mechanism toward the retrieval task before it even processes a long window. They act as a prior. The model did not need more context.
It needed an instruction, placed where instructions actually carry weight.
The prompt structure around retrieved context is just as vital an engineering variable as the retrieval itself. Where instructions sit relative to injected documents is an architectural decision.
If you put the instruction at the end of 200,000 tokens, it has a completely different effect than if you put it at the beginning. How the retrieval task is framed before the context begins interacts directly with the positional bias we outlined.
This means treating the prompt not just as a set of commands, but as a spatial arrangement. You have to map the physical layout of the text to the mathematical reality of the attention mechanism.
That's the thing. This entire architectural breakdown connects to a broader principle of research methodology. We are taught to distinguish between data availability and data quality.
Having more data does not mean having better data. A survey with 10,000 respondents and a systematic sampling bias is worse than a survey with 1,000 well-selected ones. The instrument matters as much as the volume.
Context window size is strictly an availability metric. It dictates what the model can see.
It tells you nothing about how the model will weight what it sees. It tells you nothing about whether the information you care about will receive the attention it deserves.
Reliability is determining how the model weights what it sees. That is an engineering problem requiring careful retrieval, ordering, and context structure. It is not a problem solved by scaling the window further.
More context is not more understanding. It is more input, processed by an architecture with known biases.